We're going to talk about some exponential functions. First, we're going to look at the difference between a power function, which is just a variable to any power, and an exponential, which is a constant to a variable power. And these are the ones we're going to focus on in this video. Power function would be something like x squared, x cubed, x to the fourth, etc., where the power stays constant. Exponentials has the base constant and now the power is a variable. So for example, 2 to the x would be something like 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and so on. Or we could have 7 to the x, 7 to the first, 7 to the second, 7 to the third, and so on. For exponential functions, we don't consider the base to be a negative number or 0. The base must be some positive number. It does not have to be a whole number, though. We could have 1/2 to the x. We could have the square root of 2 to the x. We can have any positive number to the x power. What I've done here is I've graphed several exponential functions. This blue one is 1 to the x power. No matter what the power is, 1 to any power is 1. And then here we have 2 to the x, 4 to the x, 10 to the x, 1/4 to the x, 1/2 to the x, and I could put in several others as well. A couple of things to notice. These rise very quickly. Another thing to notice is even though x can be a negative number, y is always going to be positive. The only exception to that is if we deliberately shift it downward. But at its base, at its core, exponential functions are always positive. They're always positive. One other thing to notice, all exponential functions go through the point 0, 1, which makes sense. If x is 0 in all of these, we have something to the 0 power. And one of our basic rules of algebra, laws of exponents, is that anything to the 0 power is 1. The only exception being 0 to the 0. That is not 1. That's an indeterminate form. Anything other than 0 to the 0 power is 1. So all of these functions have the point 0, 1 in common. And we get a sense of what the shapes of the graphs look like. If A is going to be anything between 0 and 1, like we have over here, we get a general shape like this, where the function is decreasing. As x gets bigger, the function itself gets closer and closer to 0. It shrinks. 1/2 to the 70th power. That's a very, very small number. That would be very, very close to 0. The most boring exponential function, 1 to the x, just a horizontal line. It's also the line y equals 1. And then if a is anything greater than 1, we get this shape, an increasing function. The bigger x gets, the bigger the function value gets. Couple of things with exponentials. The domain is always going to be every real number. Range, unless it's shifted, is going to be all the positive reals. Again, if we shift it downward, that's going to differ a little bit. In general, the range is going to be positive reals. And another law of exponents that you all should know by now, if we have a negative power, that simply means reciprocal. So a to the negative 3 would really be 1 over x, 1 over 3, a to the 1/3 power. Now, one of the questions is what grows faster? What increases faster, an exponential or a power function? I'm going to start with a little table. I'm just going to start plugging in values of x, and we'll see what the winner is. So we'll start with x equals 0. 2 to the 0 is 1. 0 squared is 0. So our exponential is winning. Our exponential is still winning. 2 to the first is 2. 1 squared is 1. Now we have a tie. Now the power function has tied. Now the power function has taken the lead. Now they're tied again. The exponential is caught up. The exponential has taken the lead again. And that's really the last spot where it gets close. I'm going to jump down to 10. X equals 10. Here's our exponential. Here's our power. It's not even close. This exponential starts out a little slow, and then it really kicks into gear once you get past x equals 5. An exponential function grows much faster than a similar power function. If we compare 3 to the x and x cubed, 4 to the x, x to the 4th, and so on, the gap gets very, very big very, very quickly. The exponential will always win. Exponentials grow, well, we say exponentially. That implies extremely fast growth. Or if we flip it around and have it decrease, it implies fast, at least initially, it implies fast decrease before it levels off. One of the ways you can visualize the growth of an exponential function is by paper folding. Now, there's an old myth that says you can't fold a piece of paper more than 7 times. And if you've ever watched Mythbusters, they busted that myth. The reason why it's hard to do is because every time you fold that piece of paper, you are doubling its thickness. So let's take a standard piece of paper, which is about 1/1000th of an inch thick. Actually, we haven't folded it yet. So right now it's 1/1000th of an inch thick. And we're going to start folding it and see what happens. One fold. It's now 2/1000ths of an inch thick. 2 folds. And it appears that we're going very, very slowly. And in fact, we are. However, By the time we get to the, let's drop down to the fifth fold. Which again, doesn't seem like much, but it's 32 times thicker than it was when we started. 32 times. We've increased its thickness by a factor of 32. And that makes it extremely difficult because not only is the paper itself getting thicker, but the area that we have to work with is getting much smaller. So we're trying to fold something thick in a very, very small area, and that adds to the problem. If it was possible to fold it 50 times, the thickness of that paper would be approximately 17 million miles. Let's let that sink in for a little bit. 50 folds, 17 million mile thickness. Circumference of the Earth is approximately 23 to 24,000 miles, I believe. Yeah. Let's think about that for a few moments. Reason we use exponentials, and in calculus, we use exponentials a lot. There will rarely be a day where you don't see an exponential function once we get going with things. They are used in a lot of real-life models, a lot of population models, anything that involves growth or decay, half-life in the sciences involves exponentials. There's a lot of economic models that use exponentials. There's a lot of computing models in terms of computer processor speed, in terms of decision making, in terms of number of decisions that have to be made on something called the decision tree, and so on when you're looking at how many possibilities. If you're looking at analyzing, say, a checkers board, and you're trying to think 3 or 4 moves ahead, the number of possible outcomes increases exponentially. The more moves you think ahead, the faster the number of possible moves increases. So anything involving those types of models is going to use some kind of exponential function. They are very, very common in a lot of models. And the number we focus a lot on is the number E. E, for some reason, has a lot of confusion around it. And it shouldn't. E is like the number pi. It's just a number that's been assigned a letter. We don't always say 3.14159, whatever the rest is. We just say pi. With E, we often don't say 2.718281828459045. We just say E. So what is E? Well, the best way to illustrate E is with these two graphs. Here I have an exponential function, y equals 2 to the x. And here's another exponential function, y equals 3 to the x. Now this red line is called a tangent line. If you remember your geometry, I'm going to draw a circle here. Here's a circle. And I'm going to draw a line. We may recall that this is a secant line because it goes through the circle at 2 points. And if I move this towards the edge, now it touches the circle once. It does not go into the circle. It merely touches the circle at one point and one point only. That we call that a tangent line. Here I have a similar thing. I have this curved function, and I have a tangent line that touches the function at one point. The first half of calculus, or I should say the first half of our first semester, is going to be dedicated to looking at tangent lines of functions. That's what we use to find the slope of a curve at a particular point. So without getting into all those details, we're just going to focus on what's going on here. I have a tangent line at the point 0, 1. This red line only touches the function at this point. The slope of this tangent line is approximately 0.7. Come over here, y equals 3 to the x. That's a sharper rising curve. It's steeper. It rises faster. So at the point 0, 1, the slope of this tangent has increased because this curve is rising faster. Its slope is approximately 1.1. And again, we'll deal with how do we get that number later on. It's not important for today. So I have a slope that's less than 1. I have a slope greater than 1. Here's 2 to the x. Here's 3 to the x. Is there a value of a that will give me a slope of exactly 1? Because as a moves from 2 to 3, the slope increases from approximately 7/10 to approximately 1 1/10. So I want to know what value, what constant to the x power will give me a slope of 1 at that exact point. That's the point that all exponential functions use. So what is that magic value of a? Well, that magic value of a is the value e. That's what e is. It's the exponential function that gives a slope of exactly 1 at that point. At the point 0, 1, the slope of this tangent line is exactly 1. And that's going to be an important property later on. Again, here is the value of e. It's like pi. It goes on forever. It never ends. It never repeats. Approximately 2.7. This is the amount of decimals that I had to memorize when I was in high school. It's kind of a nice little pattern, 2.7, and then it's the year 1828, 1828, and then it's a 45, 90, 45 triangle. Pretty little slick trick there. Once you get past this 5, I have no idea what the rest is, nor do I really care, because that's way more decimals than I've ever needed. 2.718 is as far as I've ever had to use it in a calculation. For our purposes, E is going to remain E. We will rarely plug in the decimal for it. But there are times where you'll need it, so there it is. That is what the exponential function is. Don't be afraid of e to the x. It's a very nice function. We will use it in many, many applications. giving you lots of opportunities to be comfortable with.